Hi, my name is Heather Harper. I'm from New Zealand and this is problem number 6, Saxon Bowl.
The problem states, a bowl with a hole in its base will sink when placed in water. The Saxons used this device for timing purposes. Investigate the parameters that determine the time of sinking. First, a definition. The bowl has sunk when water from outside the bowl enters the bowl over the top of the bowl. This is a sped up video of a bowl sinking. The actual time to sink was 2 minutes and 31 seconds. Using bowls and water as a timing device started around 3,500 years ago, with the first appearing in Egypt. The most important concept for the bowl sinking is pressure. Pressure is given by the force over the area distributed over. For fluids, we can write the mass for the weight force in terms of density and volume, giving the formula for hydrostatic pressure equals density times the acceleration due to gravity times the height of the fluid. Note that pressure is a scalar, not a vector, because pressure scales the normal force of fluids acts in all directions, so the arrows in my diagrams represent this normal force. Hydrostatic pressure depends on the depth of the water. This results in a force upwards called the buoyant force. The size of this force is equal to the weight force of the displaced water. Objects of equal volume experience an equal buoyant force, so if the object has a density that is less than water, the buoyant force is greater than the weight force. The force is balanced when the weight force of the displaced water, which is the size of the buoyancy force, is equal to the weight force of the object. For a bowl in equilibrium, this means that the mass of the displaced water is equal to the mass of the bowl. When the bowl has a hole in it, there's a pressure difference because of the height difference of water between inside and outside the bowl, so water goes through the hole. And the mass of the water displaced must still be equal to the mass of the bowl plus the mass of the water in the bowl, so the bowl sinks lower. When the bowl has filled with enough water that the volume of displaced water is under the level of the water, including the meniscus between the edge of the bowl and the water from outside the bowl can flow into the bowl, which sinks the bowl. The most important points from this are that the flow rate through the hole depends on the pressure difference, which is given by the height difference between inside and outside the bowl. The height difference depends on the mass of the bowl and the shape of the bowl. The flow rate through the hole is not constant unless the bowl is a cylinder. To model the bowl sinking, we will need a quantitative relationship between pressure difference and flow rate. To investigate how the rate of sinking changes throughout the bowl sinking, I used Tracker to track the height of the bowl above water over time. My setup was the same as in the demo video I showed at the start. For this bowl, the pressure difference is decreasing over time, but the almost straight line shows that the effect this has on the rate of the bowl sinking is slight. I will now talk about fluid flow and finding a model for the time to sink. In laminar flow, each fluid particle follows a smooth path that does not disrupt neighboring particles, whereas in turbulent flow, the flow is unpredictable because the paths cross and eddies form. Laminar versus turbulent flow is important because it limits how we can apply models of fluid flow. Reynolds number is a way of quantifying turbulence using characteristics of the object and fluid. A low Reynolds number indicates laminar flow, and a large Reynolds number indicates turbulent flow. Here are the values I used for density and dynamic viscosity of water. The diameter of the hole and the flow speed changed between tests, so I calculated a Reynolds number for every test I did. The lowest Reynolds number I got was 600, and the highest Reynolds number I got was 1900. Both are within the bounds for laminar flow. This Reynolds number refers to the flow through the hole. Above the hole, the sudden widening means that the flow rate becomes turbulent around an inner column of laminar flow. I said earlier that laminar flow was important for models of fluid flow. What we want to know from a model is, given a certain pressure difference, what is the volumetric flow rate? There are a few equations that might be helpful, of which you are looking at Pascal's law. However, all of these equations have limitations that mean we can't use them for a bowl sinking. Even if we say that the flow we are interested in is laminar, equations for fluid in a pipe assume the pipe is significantly longer than it is wide, which cannot be said of the hole in the bowl. Instead, I experimentally determined the relationship between pressure difference and flow rate by measuring the flow rate for a certain height difference. I used a cylinder because cylinders sink with constant height difference. On the left is an example of one of the cylinders I sunk. On the right is how I measured the height. If these marks are all at the same height and the 11mm mark is underwater and the 9mm mark is not underwater, the height difference is 10mm with an uncertainty of half a millimeter. I measured the time it took to sink through a certain section in the middle of the cylinder, so that the measurements we got were not affected by the hot glue at the bottom or the lips at the top. This graph shows the flow rate against pressure difference, with the colours being different hole diameters. We were expecting a linear trend, but the resistance to flow is clearly more complicated than being directly proportional to pressure difference, because the linear trends shown on this graph have significant y-intercepts. However, the data is close enough to a linear trend, although this relationship is not valid for pressure differences under 50 pascals, which is mostly below the pressure differences with which my bowls were sinking with. Each of those equations of the coloured lines means we're taking the pressure difference, times it by a gradient, and add an intercept. There are relationships, as shown in the graphs below, between the gradient and intercept of the lines of best fit and the hole diameter. So if we know the hole diameter and pressure difference, we can work out the flow rate with the equation at the bottom. Now that we know the flow rate for a given pressure difference, we can model the time to sink with a numerical model, which we wrote on Wolfram Mathematica. Given some initial conditions, we can calculate the height difference between the water inside and outside of the bowl, then the pressure difference, then the flow rate from the experiments I was just talking about, then the change in volume, assuming the flow rate will be constant over a very short change in time, then the new volume of water, then the cycle repeats. We stop when the new volume of water is greater than the volume of the bowl, minus the water displaced because of the bowl's mass. I will now talk about this step. We need to convert between a known volume of water and the height of that water. My model does that by modelling the bowl as half a sphere and the water inside as a spherical cap. These are some quick screenshots of what the model looks like. I'm about to go through the significant assumptions, but this slide has the minor assumptions, such as the bowl thickness is negligible and the flow rate is constant for the very small change in time. The model assumes that the bowl is exactly a hemisphere. Shown in the picture are the bowls I used for my experiments, and you can see this assumption will fit some bowls better than others. I also tried modelling the bowls as cylinders rather than hemispheres, but for these particular bowls, a hemisphere fits better. Another assumption is that the holes in the cylinders for the experimental relationship between pressure difference and flow rate perfectly match the holes in the bowls. This is why I hot glued metal to the bottom of the cylinders, but they still won't match the bowls perfectly. Surface tension is the adhesion between water particles, which for the water stainless steel boundary means that attraction of the water to the water causes a meniscus. The model ignores this effect, but this only accounts for a few seconds of sinking time. The biggest assumption is that the equation at the top will give the flow rate. Shown on the graph are the flow rates this predicts, along with the actual flow rates where the colours are the different hole diameters. This fits some hole diameters better than other hole diameters, and the relationship doesn't apply to pressure differences under 50 pascals because of the y-intercepts. There are also limitations on the hole diameters that can be predicted for. I will now talk about my experimental setup and process. I used a camera for the test where I could have multiple bowls sinking at once, such as volume parameter, and a stopwatch for the parameters like mass, where I use the same bowls for every test. I placed the bowls in the water by holding the bowl just over the water, then releasing the bowl. I did 5 repeats per test. The camera was positioned high up to get a better view of the bath. I used the videos to find a start and end point in the sinking times. The parameters I tested are hole diameter, bowl volume, and bowl mass. I also investigated surface tension, which I am happy to talk about in the discussion, but do not have time to go through now. First, hole diameter. It is simplest to think about the volume of water that is able to go through the hole. Area is proportional to the diameter squared. The volumetric flow rate is proportional to the area, so we expect the time to sink to be proportional to 1 over the area of the hole. This graph is the time to sink in seconds against the hole diameter. The error is half range above and below the average, as it is in all my graphs, but in most graphs the error is too small to see. This graph shows that as hole diameter increases, the time to sink decreases. The model predicts the time to sink well for hole diameters above 4 mm, but overestimates the time to sink for the 3 mm hole. The reason the 3 mm hole is overestimated is due to how the model calculates the flow rate for a given pressure difference. The lines are the relationship the model uses for each hole diameter, and the dots are the experimental values. The orange is the 3 mm holes, and you can see that the model consistently underestimates the flow rate for a given pressure difference, so will overestimate the time to sink. As you can see, when the time to sink is plotted against 1 over the whole area, we get a linear trend. I will now talk about bowl volume. When testing volume, I kept mass constant by taping the coins and weights to the bottom of the smaller bowls. Shown at the bottom are the problems I had with adding mass to the other areas of the bowls. This is also how I added mass for the mass parameter. When increasing the bowl volume, the height of the bowl also increased, both of which increase the time to sink. This fits the model because for a hemisphere to have a larger volume, it must have a larger radius. This graph shows that as the volume increases, the time to sink increases. The model predicts the times closely, except for the largest bowl. This is because of the pressure differences with which the largest bowl sinks. It has a relatively low mass and large radius, so just before it sinks, the pressure difference is only 44 pascals. This is in the red area of the graph shown, meaning a linear trend isn't valid. The flow rate is overestimated, and therefore the time to sink is underestimated. I will now talk about bowl mass. Increasing the mass of the bowl means the bowl displaces a greater volume of water as it sinks. This means that the height difference and therefore the pressure difference is bigger, but it also means that the bowl doesn't have to fill up as far before it sinks. This graph shows that as the mass of the bowl increases, the time to sink decreases. The model shows a similar trend, but underestimates the time to sink by about 20 seconds every test. A few seconds of that can be accounted to the model ignoring the meniscus formed between the edge of the bowl and water. Given the discrepancy is similar for all the tests, the rest of the difference will be due to the assumptions matching the bowl, including how closely the bowl matches the hemisphere and the imperfections of the hole. In conclusion, objects of equal volume experience equal buoyant forces, so the volume of displaced water is equal to the mass of the bowl plus the mass of the water inside the bowl. This creates a height difference and therefore a pressure difference between inside and outside the bowl, so water goes through the hole. The fastest sinking time will be when a bowl has a large hole diameter, small volume, large mass, and low surface tension. Acknowledgements, references. Thank you.